We're going to go ahead and take a look at z-scores and what they are, but we're going to do a little bit of background on that first. We're going to look at density curves. A density curve is a mathematical model that's always above the horizontal axis, and the total area underneath this curve is always equal to 1. And it tells you the proportion that relates to what you're dealing with. So these are examples of density curves. For the most part, these are bell-shaped curves. Now, they could be given to you, you could graph these using this equation here, where or not but pi is in the denominator here in a root. You have your natural number e, which ties into our logarithm stuff that we did a little bit ago. Now, this mu happens to be the mean or the average, and then this funny looking sigma with 0 with the tail on it is your standard deviations, which we're going to be talking about here. But it's interesting, this thing here has e and pi both in it, even though you wouldn't necessarily think of that. Now, your mean, mu, is always at the center where the peak is. Your standard deviation, if it's bigger, it's more spread out and not as high in the center, but wider. If your standard deviation is smaller, it's narrower and not nearly as spread out at the bottom. So standard deviation, for the most part, is how spread out your data is, or how far you are from your mean. Now, if you go one standard deviation on each side of your mean, so if your mean is 0, you go one standard deviation to the right, one standard deviation to the left, that contains 68% of your data. Because remember, everything underneath your curve here ends up being 1. Now, if you go 2 standard deviations to the right and 2 to the left, that's 95% of your data. Or if you go 3 each side, that's 99.7% of the data. If you take stats, you'll end up dealing with that a lot. Now, at 1 standard deviation is your inflection point. And if you were to take calculus at some point, that will tie in to what you're dealing with in calc. So the rule that we were just talking about is often referred to as the 68, 95, 99.7 rule. So 68% of your data is within 1 standard deviation of your mean, 95 within 2 standard deviations of your mean, and 99.7% of your data is within 3 standard deviation of your mean. Now we're going to get into z-scores, and that's going to be the main focus here. And it does tie into your density curves that we just talked about. A z-score measures how many standard deviations a certain data value is above or. So to figure out how many standard deviations, you take your data value minus your mean divided by your standard deviation. And that tells you how many standard deviations you are above if it's positive, or below the mean if it's negative. So suppose we have an ACT score. It's normally distributed. That's your bell-shaped curve. It's got a mean of 500 and a standard deviation of 100. And the student gets a 700. What is their z-score? So we take our data value of 700 minus our mean of 500 over our standard deviation. We subtract the top, we get 200 divided by 100, and we get 2. That's a positive 2. So when you're looking at your bell-shaped curve, here is positive 2. Now, a positive 2 means they did better than all this shaded in pink over here. So all this is the people that did less than that 700, or a z-score of 2. What's to the right over here would be all the people that did better than that z-score of 2, or better than a score of 700. So that's how it ties into the normal density curve. Now we're going to also explore table A. which is in the back of your notes. You'll also be given this table when you take a quiz or a test on this stuff. So don't be concerned about memorizing it. It would be a challenge to memorize. Now, a lot of times z-scores don't work out to be a nice, neat number like just 2. Now, suppose you had a z-score of negative 2.40. So you go to negative 2.4 in the left-hand column, and then you go to where your second decimal point, which is 0, is right here, and you get a z-score of this. If you had a z-score of negative 2.41, you go to still negative 2.4 here, but you'd have to go to the O1 column, so your second decimal point. And this table always tells you the amount of area on your curve that we were just looking at that occurs to the left, or that is less than that. So if you're looking at negative 2.46, you still go to negative 2.4, go across that row until you get to your O6 column. So that's how you end up using this table. So once again, your standard normal table always tells you the proportion of data that's less than whatever z-score you ended up getting, or that shows up to the left on your curve. So consider this. We have a math test with a mean of 70 and a standard deviation of 8. We have an English test of a mean of 74 and a standard deviation of 16. Suppose somebody got a 78 on each one. Well, which test did they really do better? Yes, the means are different, but the standard deviations are also different. So we could do our z-score for the English, and we could do our z-score for the math. So we take our English 78, because that's what they scored, minus our mean of 74, over our standard deviation for English, which is 16. Work that out, oops, and we get a quarter. And we do the same thing for math. We take our 78 minus our mean of 70 over our standard deviation for math, which is 8. That gives us 8 over 8, or 1. So we would say the math did better because they had a standard deviation of 1, where English only had a standard deviation of 4. So 1 would be over here, which means you're farther to the right than you would be if you were at a quarter, which would be back here. Farther to the right means you are better than more of the anything that's to your left. So consider we have this. We have 17 is your mean. We have a standard deviation of 2. And we want to know what's our height if it's less than 14.1. So we have our mean of 17. We have 14.1 is our data value. Our standard deviation is 2. And we get negative 1.45. So we'd have to find that in table A. So you would go down to negative 1.4 in the left-hand column, and then you would go over to the O5 column here, come down to see where they cross, and you would get this. That's what we're going to look at. So 0.0735 of your data is to the left. That's in the shaded here area. So your z-score goes across the bottom, so about negative 1.45 is about here. So this little shaded tail has an area of this. So if you wanted to change that to a percentage, you could. You could say, well, 7.35% of your data is here. Well, if all your data is here, you could easily then figure this out by subtracting that from 100 if you wanted. But we weren't looking for that because we were looking for what's less. And table A always tells you what's less. That's always to the left of this value in your tail. So what about being more than 12? Well, 12 minus 17 over 2, negative 2.5. So our z-score is negative 2.5. So we go to negative 2.5 here, go to the OO column here, and we get this. So this red tail has an area. I thought I hit that color, sorry, 0.0062. But we want, according to this up here, we want more than. So that means what we have here in red is less than. We want more than, so that would be all this right here. This would be all that area. Well, remember, the whole area is 1. So to figure out the blue, if you know the red, is just subtract the red from 1, and it tells you what's left over for your blue. So if you're looking for what's less than, it's just what's in your table. If you're looking for what's more than, you got to do what's in your table, do all that work. Sorry about that. And just go 1 minus what was in your table if you're looking for more than. So what about if you're looking for in between? So here we have a mean, we have a standard deviation, and we are looking for what's in between 12.0 and 12.02. So if you're looking for the 12.2, you do your normal work, your, oh, sorry, I flipped that around. So we go 12.2 minus our mean over this gives us 1. If we do our 12, we go 12 minus our mean over 0.1. Now we'd have to go ahead and look each one of these up in our table. So 1.00. 1.00 would be this number here. Then you'd have to look up negative 1.0. Well, let's see, that would be this number here. Now, we're looking for what's in between. So if we look at this right here for this first one, that would be this right here. When we're looking at the blue, that would be telling us this. We're looking for what's in between, so we'd want to take the whole thing kind of in the maroon color minus our blue thing, and that would tell us what's left over for our green. So you'd want to go ahead and subtract these two to get this. So if you're looking for what's in between, you still work out your z-scores and you get stuff from your tables, and you subtract the numbers in your table.